right, physical geology class. Let's go over running water, chapter 16. Earth, it's a very unique planet. It's kind of like in the Goldilocks range in terms of distance from our medium-sized star sun. And it's the right size to contain liquid water, which is crucial for life on Earth. Mantle convection, or just circulation, or the transfer of heat through the mantle, what drives plate tectonics, brings a lot of water to the surface of the Earth through outgassing in volcanoes. And so that's how a lot of water was kind of delivered to the surface of the Earth. And the hydrological cycle essentially describes how water moves through the four spheres we've talked about in the beginning of class: the geosphere, hydrosphere, atmosphere, and biosphere. So the majority of water on Earth resides in the oceans, and it's salty, 96.5%. It's a lot. Okay, the rest of the water here, about 2.5% is fresh water. That's it. Of the fresh water, so of that 2.5%, most of it is locked up in glaciers and ice sheets, about 68%. The rest is groundwater. All right, that's our next lecture. And then only about 1.3% of that is surface water. And then if you go to surface water and break that down, that 1.3%, most of it, 73%, is snow and ice. 20% is our lakes, are found in lakes, that water. 2.5% in swamps, 3.5% in soil moisture, and this rounds out the rest. Ooh, biological water. So the hydrological cycle basically shows how water moves through all these different reservoirs. Water evaporates from the oceans, plants transpirate water, and water evaporates from soil and moves up into the atmosphere. And water leaves the atmosphere via precipitation. So that's either snow or rain or sleet. And then precipitation either soaks into the ground and becomes part of the groundwater reservoir through infiltration. It can run off the surface of the landscape. We call that runoff. It can also evaporate back into the atmosphere. Or it's stored in a snow field or glacier. All right, so the hydrological cycle is balanced. Water is just moving from different reservoir to another, but the total amount of water essentially remains the same. So here it is. About 320,000 cubic kilometers are evaporated from the oceans every year, approximately. About, what is that, like maybe 70% of it just rains back on to the ocean as precipitation or snow. And then the rest, 96%, precipitates on land. And then about 60,000 cubic kilometers are either evaporated or transpirated back into the atmosphere. 36,000 cubic kilometers then runs off, goes back into the ocean, and then some of that water kind of meets up in the ground as part of the groundwater system. So transpiration involves water being absorbed by plants and then transferred to the atmosphere. Plants need water. And so evaporation and transpiration are essentially the same thing, just water being converted from its liquid phase to the vapor phase. So we kind of word smash those together and call that evapotranspiration. So the difference between runoff and infiltration when you have running water on the Earth's surface really depends on, like whether or not when it rains, whether water will run off or soak into the ground depends on the intensity and duration of the rainfall. If you have very light rain, a lot of that's just going to stick to the ground surface and slowly infiltrate downwards. If you have long-lasting and intense rainfall, it'll saturate the upper layer of the ground quickly, and then most of that water will run off. Also, if the ground is already saturated, that means all the new precipitation will run off as a result. The type of soil, if you have sandy soil, that will allow water to penetrate or infiltrate through it easier. If your soil has a lot of clay in it, clay acts like a kind of barrier, so it'll force the water to kind of run off the clay. Also, the slope of the land, if you got flat land and it rains on it, the water will just pool on top of it and slowly infiltrate through the ground and evaporate. But if you have steep land, then that water will run off. And also the nature of vegetative cover. If you have a lot of plant cover, that'll absorb a lot of water. The water can trickle down through the roots and get to the ground, beneath the ground, a little easier. In kind of desert landscapes where there isn't much vegetation cover, a lot of water will run off as a result because of that. So when the surface is impermeable or saturated, runoff is dominant. So in urban areas like cities, due to buildings with impermeable surfaces and roads and parking lots, that diverts a lot of water into drainage areas, and that creates a lot of runoff. So runoff starts off as sheet flow, and sheet flow turns into tiny little channels and rills, and then rills form to meet gullies, and gullies form brooks, creeks, and streams. And the stream is any water that flows in a channel regardless of the size. And then a river carries a substantial amount of water and can have a lot of tributaries. A drainage basin is essentially an entire area that contributes water to a channel or a stream. We call this a watershed. So drainage basins or watersheds are divided by these imaginary lines, typically areas of high elevation. We call those divides. A lot of times they're high ridges and mountainous areas. And in subdued topography, much like Florida, that may be hard to distinguish. And if we have very large watersheds or drainage basins, a continental divide will split an entire continent into different drainage basins. And I'll show you an example of that with the Mississippi River Basin. And if you observe streams over years, what you'll see is that a lot of times they lengthen their courses, and they lengthen their courses via the beginnings of the river. The beginnings of the river are usually called the headwaters, right? That's typically up at higher elevations where a bunch of tributaries kind of meet into the main artery of a river. And they erode along those areas, and we call that headward erosion. And I'll show you an example of that as well. So here's an example of a drainage basin. All right, so this entire land area over here, let's try a thicker one, see what this does. Oh God, that's a highlighter. This entire land area over here contributes, if it rains here, all that water will kind of divert itself and run off into this stream here. And what separates the different drainage basins is the divide right there. Okay, let's go with the thinner one here. All right, and then this is the Mississippi River Drainage Basin is the largest drainage basin in the United States. If it precipitates anywhere in this area of all these kind of subdivided drainage basins, that water will run along the Mississippi River and dump out into the Gulf of Mexico. This place is huge, this Mississippi River Drainage Basin. And the continental divides are, they run along this area here, and it goes right through Yellowstone National Park. That's what this image is here. And also along the Appalachians over here. So those are continental divides that separate larger drainage basins. And then here's what I'm talking about with that headward erosion business. Here's the beginnings of a river or tributaries that feed into the San Rafael River. So the erosion continues this way. So this is headward erosion. So erosion is going to continue in this direction and lengthen the course of this river. So river systems drain much of the land area. So there are very few exceptions to this. Deserts and polar regions that don't receive a lot of precipitation, so it wouldn't be true there. And the variety of different types of rivers is a reflection of the different environments that they're found in. And human intervention and climatic differences can alter the character of a river. And a river can be divided up into 3 zones: the production zone, transportation, and disposition. The sediment production zone is typically at the headwaters of the river, the beginnings of the river, the area where the river begins up in the mountains or at a higher elevation. This is where most sediment is derived because that is where sediment is mass wasting and then is carried by the river, essentially downriver. Okay, and that sediment is generated by chemical and physical weathering, bedrock broken into smaller pieces, erosion, and scouring of that bed channel. The transport zone is kind of like the middle of the river. This is where sediment is transported in suspension in the river, and an equal amount of sediment is being eroded and deposited in the sediment transport portion. And the sediment deposition, this is where rivers ultimately meet their end, which is another large body of water. Could be a reservoir, or most of the time it's the ocean. And so what happens is the velocity of the river slows down, and then all the suspended sediment particles settle out and deposit, and they create depositional features. So here we are. Here are the headwaters. This is a zone of sediment production. So a lot of erosion occurs here. That's where sediments are generated, and then they're essentially brought down by the river like a conveyor belt. Here's the zone of transportation. So you have equal amount of deposition and erosion in these areas. And then here's the mouth of the river, or the river's end, and that's where you'll find deltas and a large amount of sediment being deposited in these areas. So there are many distinct drainage patterns. Drainage patterns are just interconnected network of different streams that kind of come together and feed a main river. There are 4 main common drainage patterns. Let's just jump right to the image. This is the dendritic pattern. So water starts in these smaller areas here, these distributaries, and then these little streams. They all feed into the larger kind of main artery here. It's almost like a tree without any leaves, tree in the fall. And so the direction of the river flow is this way. Okay, and then all of this contribute. This is the most common pattern. Okay, and this happens when the surface material or the exposed rock is uniform. You can also have a radial pattern. Okay, and if you have a major landscape feature like a volcano, essentially the water will channelize and move away from that large feature. So you can see they're all kind of radiating away from the volcano. Then there's the Minecraft river here. This is called the rectangular pattern. Okay, and the river basically follows along a highly jointed bedrock, and that's why it has that kind of rectangular pattern. And then the trellis pattern, this is where you have exposed rock with differing resistance to weathering. So you have weak rocks and then highly resistant bedrock. So here, this right here is the highly resistant rock. Maybe it's like quartzite or something, as well as here. And in between those ridges here, this rock is a little more less resistant. And so the water kind of rolls downhill and then flows along the less resistant rock. And then it finds one way to jump the gap past the very resistant rock over here. And we usually call those water gaps. Okay, so this area here would be a water gap. They're nice places to visit because sometimes you can see waterfalls or fast-moving water as it moves to the next less resistant area over here, and then the water just jumps the resistant bed once. Sure, maybe you've been on a family vacation, be like, oh, let's go stop at the water gap off the highway. All right, stream flow. Water moves in the river channel under the influence of gravity. So if you have water flowing in a nearly straight path, maybe like the Florida Everglades, we refer to that as laminar flow. When you have water kind of turbulently moving in an erratic fashion, back and forth, smashing into rocks, horizontal, vertical movement, we call that turbulent flow. And streams typically exhibit turbulent flow. So laminar flow is kind of the exception. So here, very lazy river over here. Here's primarily laminar flow. That means the gradient is very low, aka Central Florida all the way down to South Florida. The Everglades is a slow-moving river, laminar flow or sheet flow. And then this is extreme turbulent water, Colorado River, woo, Mountain Dew. All right, so the factors that affect the flow velocity of water primarily is the gradient, right? So if you have a steeper landscape, you'll have faster moving water because it's under the influence of more gravitational energy. So that drives the channel flow. But also the channel shape's important. The bottom or the river channel, the bottom of the river, there's this idea called the wetted perimeter, and that's the area of the river that's in contact with the channel. And if you have a cross-section of a river, a really wide river, more of the water is its surface area is touching the channel in a wider channel. So that creates more resistance and that slows down the water. If you have a narrow, deeper channel, that there's less surface area that's touching the water and slowing it down via friction and resistance. So here's that really wide river. And so if you measure the actual surface that's coming into contact with water, more water is rubbing against the channel floor and the walls essentially, and that slows down the water. Okay, but if you have a narrow channel, and this is narrow and deeper, less surface area is slowing down the water, and therefore this water flows faster. Now, other factors that affect stream flow, the roughness of the channel. Okay, so if you have boulders or rocks that create turbulence, that kind of slows down the water velocity. Think of it as like the aerodynamics of the channel, and channel size, essentially. So if you have more water flowing through the river, that's a higher discharge. That's going to make the stream flow faster. All right, discharge is the volume of water flowing past a certain point in any given unit of time. All right, so when you increase the discharge of the river, the width, the depth, and the flow velocity increase. Imagine holding a water bottle and just slowly pouring out the water, or just turning it completely upside down and creating a lot of water coming out at once. You're creating more discharge coming out of the bottle, and that increases the flow velocity of the water. And this is important to monitor this stream flow in rivers across the United States. And that's why we have a governmental agency that does this. The U.S. Geological Survey measures the flow velocity, discharge, and the river stage, which is the height of the water surface in a river, in over 7,500 stream gauging stations. And that data is really useful for water management purposes. The reason people are interested in that kind of data is so that we can warn cities that might be in floodplains or in low-lying areas of an incoming flood. For example, I don't know if you remember Hurricane Florence that came in and ravaged the Carolinas. Well, Florence brought in a lot of coastal flooding as a result of storm surge, and then kind of went inland and just dumped a lot of rain over the Appalachian Mountains, right? And so the people in coastal Carolina dealt with the initial flooding from storm surge, right? All that precipitation. And it took 9 days later for the crest of all that water to come down the mountains and then flood them again. So not only did they have to deal with a natural disaster and a hurricane, but then 9 days later they had to deal with flooding because of all the water that was kind of rained on in the drainage basins of the Appalachian Mountains, kind of coming downhill, essentially. So this has to be tracked. Here are all the gauging stations. Okay, here's an example of a gauging station with 2 cable towers and a car. This measures the discharge, or the volume of water flowing through an area in any given amount of time. And then there's a well, and a well will read the river stage, which is the kind of level of the river. So the longitudinal profile of a river is essentially kind of looking at a river in cross-section from head to mouth. The head is the headwater regions of the river, the beginnings of the river, and the mouth is where the river meets the ocean. So most longitudinal profiles of rivers have a kind of concave shape, and I'll show you one. And so what happens is discharge increases towards the mouth. It's kind of like a bottleneck idea where the water slightly slows down in velocity, and then more water is being collected from all the contributing streams into the main river, and so there's a larger volume of water flowing at the mouth of the river. The channel size and velocity also increase towards the mouth because of that increase in discharge. However, the slope decreases, so the gradient decreases, and the volume of water increases downstream. Okay, so here's that longitudinal profile. Here's the head in terms of elevation, obviously much higher. And then as we go along the river, if say we're rafting on this river all the way down to the mouth, you'd be going down in elevation. And so you can see that the gradient shifts greatly once you get down to closer to the ocean. And so here's the example. Here's the Kings River in California. Its headwaters are in the Sierra Nevada mountains, and then all this water kind of moves down the steep gradient into the Central Valley of California, and the river as a result gets wider, and there's more discharge down here. So here are the changing factors. Channel roughness decreases as you approach the mouth of a river, and that's because here you have more bedrock being exposed, so that's really rough channels, and then here it's more sediment being deposited, so it's kind of flowing on top of sediment. Obviously the slope or the gradient decreases. Discharge increases, so the amount of water flowing through the area increases as you go to the mouth. Channel size also increases, and the flow velocity increases just slightly. So running water does a lot of work, does a lot of erosion, okay? And the erosion is related to the slope, the amount of discharge, and the sediments that are in there. And so sand-sized particles are eroded very easily. Silt and clay are a little harder to erode because they're kind of like flatter, okay? Channels that have silty bottoms are typically more narrow than sandy channels as a result of their erosive capabilities. But streams cut through these channels by abrading, quarrying, and corroding the rocks that are underneath them. And quarrying really is the removal of large blocks from the channel bed, and that can typically happen during a flood stage when the discharge of a river is really high. So by scraping, bumping, and rubbing and abrading, both eroding sediments and polishing them as they're moving them down. I don't know if you've ever been by a river, but if you notice, a lot of times the deposits of pebbles and stuff like that are rounded because of this. Potholes can form. Potholes are when you have bedrock or running water that's in the channel running on bedrock, and then the river is kind of carrying larger kind of gravel or pebble-sized sediment, and that abrades the bedrock. And sometimes it can happen in a circular motion, creating these holes or these potholes, as they're referred to. Okay, I have a picture here. So yeah, so if you have circular motion of these small kind of gravel-sized rocks, it can create, that motion can abrade the existing bedrock and create these potholes. Nice little cold water jacuzzis for you. Okay, so the running water does a lot of work. It transports a lot of sediments. Okay, all streams transport some type of sediment, and that sediment load, that's what it's referred to as, like a load that it's carrying, can be transported in three ways. One, in solution, we call that the dissolved load. So that's the invisible load that's in the water. Think of ocean water, right? Ever been to the ocean and taste that water? It's disgusting, right? You know why? Because it carries a lot of dissolved solids in it. So you don't see the dissolved solids in seawater, but it's there because you can taste it. River water also has dissolved solids in it, just not as much as the ocean. And so that's why it doesn't taste salty, but they're there. Rivers also carry sediment in its suspended load, or in suspension. This is just stuff that's floating along in the river. I don't know if you've been to many rivers, sometimes you can see like the water's just straight brown. That's just clay sediment that's in suspension. So rivers are essentially like conveyor belts, and they just help transport sediment downhill to depositional areas. And then there's the bed load. This happens along the channel of the river, and this is sliding, skipping, or rolling of rocks at the bottom of the channel. Okay, so here's your invisible load in the water. Your suspended load is all the water that's in suspension floating along with the river, and then the bed load's at the bottom with all this bouncing and sliding. Okay, so most of the dissolved load in rivers is delivered to the river via groundwater. So groundwater contributes water to streams. Okay, dissolved load is not affected by stream velocity. So you can have a slow moving river or a really fast moving river. That's not going to change the dissolved load. The only time the dissolved load can change is when you have organisms creating hard parts. Like say you have some sort of clams or snails creating their shells from the river water itself. That can remove calcium, which is a dissolved solid in water. And that can change the composition of the dissolved load. Or if you have a lot of evaporation. So say this river is kind of flowing through a really dry area and a lot of the water is evaporating. So what will happen is the concentration of the dissolved load increases only because you're removing pure water from the river itself via evaporation. The suspended load, this is the largest part of the stream's load. It carries all this sediment in suspension. Okay, it's typically very fine sand, silt, or clay, and that's the stuff that's floating kind of in the water. Imagine like throwing goldfish flakes in an aquarium, and you see how they're kind of slowly floating around. But imagine moving water carrying that stuff as it kind of goes downriver. During flood stage events, so in the spring when there's a lot of meltwater, or if there's a low pressure system that dumps a lot of rain, suspended load can carry very large particles in suspension, even boulders in some cases. Well, boulders would move down, slide down, so that'd be the bed load, but you get my drift, like maybe pebbles or something. And so the amount of material carried in suspension is directly related to the velocity of the water itself, so the stream velocity. The faster moving water you have, the larger particles the river can carry. And so we refer to this as the settling velocity of different particles. Okay, let's take a look at that. Look at this river over here, brown, Yahoo colored, just chocolate milk covered river, right? So here, this is a muddy river, right? And so it's carrying a lot of fine sand, silt, and clay, okay? Here is a graph showing you the particle size, okay? Clay being the smallest, then silt being slightly larger, sand and coarse material. This is the diameter of that material in terms of millimeters, okay? So here's 100 millimeters down to 0.001. And then here on this axis is the flow velocity. And so you increase as you go upwards. And what you notice is this line here, this is the settling velocity of all of these particles at different velocities. So if you have, let's pretend you have water moving at 100 centimeters per second. So here's your water moving at 100 centimeters per second. That's an entire meter every second. That's going to keep all of these particles basically from here on down in suspension. Okay, because it intersects the settling velocity right here. So basically if we draw that down, all the particles over here will be in suspension. Anything about maybe, what is that, like 15 millimeters in diameter will be in suspension if you have water moving at 100 centimeters per second. Now let's erase that. Let's say the water velocity drops from 100 centimeters to about 10 centimeters per second. So we draw a straight line over here, right? And then wherever it intersects the settling velocity, then you draw a straight line down. Now, any size particle from sand all the way down to clay will remain in suspension, but see, all the particles from here to here will settle because the water is not moving fast enough to keep it in suspension. So then if you continue to do this and water continues, the velocity of water decreases to 0.5 centimeters per second. Now only silt and clay will remain in suspension and all the sand will deposit out. Okay, so that's the take-home message. Faster moving river water carries larger particles. And as soon as the velocity decreases, the material that's in the suspended load will deposit out. A lot of times they'll deposit in areas like this. Here's a sandbar as an example. And then the bed load here, this is material that's kind of bumping on the bottom of the channel. And the process is called saltation. as these large particles kind of roll along the bottom of the river. Okay, there's two terms that describe the stream's ability to carry solid particles. One is capacity. That's the maximum load of solid particles a stream can carry per unit time. This is related to discharge. Okay, so a river that has great capacity is a river that's got a lot of water in it. So it's the maximum load of particles, meaning like if you've got more water, it's carrying more sediment. So like the Mississippi River, for example, I don't know if you've ever seen it, not the fastest moving river, but it's wide. It's super wide, and there's a huge volume of water moving through it. So its capacity is immense, okay? Competence has to deal with the maximum particle size. So the Mississippi River, although it's so big and there's a lot of volume of water, its competence isn't that high. It's not very competent because it can't carry larger particles. Maybe other rivers that are faster flowing and more turbulent, those are more competent because they can carry larger sized particles. All right, let's talk about some of the depositional features that are left by a stream. So deposition occurs when the stream's velocity is decreased. So particles start depositing into an area. Here is a river where all this, it's a dried out river, so it's an ephemeral river, but here's where the river channel is, and you can see all the sediment that's been deposited by this river. Okay, we call any sediment deposited by rivers, we call that alluvium. All right, and if particles of the same size, like say all sand sized or all silt or all clay sized particles, if they're all deposited at the same time, we call that sorting or well sorting. Okay, and typically largest particles settle out first. There are different types of channels. Bedrock channels are river channels that cut right into the geology of the region. These are typically at the headwaters, and what you see at bedrock channels, like you see this in this picture here, you tend to get energetic flow, faster moving water. You can see sometimes waterfalls, steps, pools, potholes forming. And this pattern is controlled by the underlying geology because it essentially erodes straight to the underlying geology. Alluvial fans are a little different. This form when sediment is previously deposited in a valley. So it's typically associated with a floodplain, very broad and flat area where water kind of meanders through. Okay, so channels here can change shape as they erode and deposit material. And so these channel patterns reflect the stream's ability to transport load at any rate. Okay. The first type of alluvial channel is a meandering channel. Okay, this is where streams transport, or these are like rivers kind of evolve into these huge meandering sweeping bends and loops. Okay, they're relatively deep, smooth channels, transport a lot of mud, and they evolve. These rivers evolve over time, and they are constantly changing. So what happens is you have, let's say, let me draw a meandering river over here. This is what's happening, these loops back and forth like this, okay? The outside of a meander is called a cut bank. So let me just change the color on you here. This area of the river would be referred to as a cut bank. Okay, so this would be a cut bank, all right? And that's an area of active erosion. So what will happen is that the meanders over time will evolve and become larger and become even more sweeping back and forth like that. So it kind of like the river kind of widens a valley, okay? The inside of a meander is called a point bar. So that's the exact opposite area. So if this area here, if this area here was a cut bank, this area over here would be a point bar, and that's where deposition occurs. Okay, let me just go over here. I think it's easier if I just use their image. So here, this is a cut bank, and the reason why it's a cut bank and erosion is occurring here is because the water velocity hits its maximum as soon as it hits that curve. So not a good idea to build your house on a cut bank because your house will just fall into the river via erosion. Okay, so when you have maximum velocity next to the channel wall, you'll have a lot of erosion. Now the exact opposite end of a cut bank is a point bar. So this area over here is the point bar. This is where you have the lowest velocity of water. And what happens when you have low velocity? Well, deposition, and that's why we have these sandbanks. If you look here, this is an aerial shot. You can see the sandbanks here. This is a point bar. Here's another point bar, right? And then here's another point bar. That's where you have deposition. And then the cut banks would be over here. And so what happens over time is these cut banks get larger and larger, and they erode in this direction, right? And what can happen is if you have two cut banks kind of really close together, here's a cut bank, right? And here's a cut bank. So they're eroding towards each other. What will happen is the river will just jump the bank, and then you create a cutoff. And then what you're left behind with is like an abandoned oxbow lake. So it's a horseshoe-shaped lake that ends up becoming a swamp, where the river used to kind of, this is one of the bends that it used to create, but because the two point bars kind of, two cut banks met each other, now the river kind of narrowed, right? So this is how meandering rivers evolve. They widen, or their meanders widen and widen and widen, and then they form a cutoff, and then they narrow, and then they widen, and then they narrow, and then they widen, and then they narrow, over and over again. And that's how these rivers kind of continuously evolve and change and alter the landscape through time. Oh, awesome. This is a really cool GIF showing you that process. Okay, so focus on, let's erase this material here. Okay, focus on this area right here. All right, if you notice, see this oxbow formed right here? This was one of the meander loops. Two cut banks, they reached each other and they cut off, and it left this kind of meander on its own. I think there's another meander that gets cut off right over here. This whole thing gets cut off. So the river kind of widens. It almost looks like a snake. But yeah, this is how this thing evolves over time. Wow, I'm impressed by my work. Anyways, there's another type of alluvial channel called the braided channel. And a braided channel is when a river hits like a low-lying area and it moves through an area that was formerly cut by glaciers and where glacial till and sediment had been deposited in this valley, where like glaciers end. Glaciers are kind of like huge bulldozers where their blade just pushes a lot of sediment, and at the terminus of a glacier it just leaves a huge pile of sediment. And just imagine now a river cutting through all that sediment. Okay, so this has highly variable discharge, and it typically forms at the toe of a glacier, the ending of a glacier. So here, the reason why it's called braided is because it has a bunch of just braided kind of all these different pathways through the unconsolidated sediment in a kind of low-lying area. So how do rivers shape stream valleys? They do a lot of work, and a stream valley is the channel and the surrounding terrain that directs water into the stream. So alluvial channels like the braided channel the braided channel and the meandering channels, those stream valleys have very wide floors. Excuse me. And bedrock channels, which are different from the alluvial channels, which are usually at the headwaters, they tend to have narrow V-shaped valleys. Okay, and in arid climates, that is exacerbated. So these V-shaped channels create slot canyons, which are very impressive. I think I got a picture. Here we go. Here's a slot canyon. The narrows at Zion National Park have a slot canyon, or that slot canyon has the vertical walls are about like 2,000 feet, which is incredible. So this would be considered like a V-shaped valley. Okay. So how do these stream valleys, how are they shaped? Well, it's through erosion of the running water. And so what occurs here is there's something called the base level, and that's the lowest point to which a stream can erode. Okay. Almost all base levels are sea level. We call that the ultimate base level, but there can be local or temporary base levels. And that can be lakes or other large rivers, or even any area where we've set up a dam, for example, to create a reservoir. That can be a local temporary base. And when there are changing conditions, that adjusts the stream's behavior. So you can raise the base level, that causes deposition, or if you lower the base level, that causes erosion. So let's take an example here. Here's a river. This is the ultimate base level. When you're close to the base level, the river will be more like an alluvial channel, meandering back and forth. But as you go further and further away, see, look, if you draw the base level underneath here, oops, that was not straight. Here you're at a higher elevation. So here the channel is straighter and doesn't meander. And so the water's focused on erosion and cutting downward. Here the erosion is focused on a side-to-side kind of meandering type because it's closer to the base level. But let's pretend we built a dam, all right? And so what happens here is this is the new base level, okay? So you kind of raise the base level here. So what'll happen is that this area, this part of the river, which was really narrow and focused on downcutting and erosion, since it's close to the new base level, it's going to instead start to meander back and forth because this is the new base level. Okay, so you'll change the characteristics of a river by altering the base level. So what happens is valley deepening occurs in young rivers or at the headwaters where there's a steep gradient. So the channel is very far away from its base level and the river focuses its energy on eroding downwards. And what that creates are V-shaped valleys. And that's the result of severe downcutting. And these are the rivers where you see rapids, waterfalls, and V-shaped valleys. A great example of this are the steep valley walls of the Yellowstone River. Remember, this area of Yellowstone's at an elevation of about 12,000 feet. So that water is really far away from the base level. So it focuses on eroding downwards and cutting downwards. Okay. Here's an example also of erosion downwards. This is the present position of Niagara Falls, right around here. But Niagara Falls used to be right at the Niagara Escarpment as it dumps water from Lake Erie into Lake Ontario. But because of that erosion, headward erosion, the falls itself erode the rock. And the falls have traveled over 7 miles to its current position over the past 12,000 years. So Niagara Falls has kind of retreated backwards and will continue to retreat backwards as it continues to erode. Don't worry, there's no rush to get married and go check out Niagara Falls. It'll still be there. This is geologic time scales we're talking about. Yeah, there's laughter back there. I can hear it. Other rivers focus on eroding side to side or wide valley widening. Okay, so when a stream approaches the ultimate base level, downcutting is less dominant, and now instead the river kind of sways back and forth. That's where those meanders come from, and more energy is directed side to side, just kind of lateral erosion. And so what that creates is a flat valley floor or a floodplain. Okay, so think of the Mississippi River floodplain, closer to the Gulf of Mexico, lower elevation, and that's why you have that. And so floodplains will be inundated or flooded when the stream is in its flood stage and water overflows its banks, and it creates different situations here. Let me show you. So here's the kind of evolution of a river. Here's a young river downcutting, trying to get to the ultimate base level. So it's focused on creating those V-shaped valleys and downcutting erosion. But over time, once it gets to the base level, then the river meanders back and forth and starts widening and eroding these areas of the valley and widening it. And here's a well-developed floodplain. After hundreds of thousands of years of a river kind of evolving and meandering back and forth, creating those oxbow lakes and depositing material, it's going to widen the valleys here and create a nice, beautiful floodplain. In some rare instances, there can be something called incised meanders. Incised meanders are essentially when you have a meandering river that's very close to its ultimate base level, but something changes the base level. And it could be something natural like uplift, for example. So the Colorado Plateau is the perfect example of this. Like if you go to the Grand Canyon or if you go to Utah, they're at higher elevations. The Grand Canyon is about 8,000 feet of elevation, but that used to be at sea level. So the Colorado River used to dump its water into the ocean, at sea level, and so it was a meandering river. But what happened was the entire plateau was uplifted over the past, let's say, 20 million years, uplifted, and so the erosive power of the river, instead of being lateral, started focusing downwards, but it kept its meandering shape. Okay, so here it was, the Colorado River kind of meandering back and forth and back and forth, but then there was substantial uplift. So then the river just started carving downwards. So it kept its meandering kind of back and forth loops, but now it created kind of very steep canyons, which makes this a very impressive view. This is Canyonlands National Park. It's beautiful. And then if this happens repeatedly, you can create an initial floodplain, and then as an area is slightly uplifted, the river will create a new floodplain and leave behind its former floodplain at a higher elevation, and we call this a terrace. And this can happen repeatedly, and you can have multiple terraces forming of areas where that used to be the base of the floodplain, but because of slight uplift, now you have kind of little stepwise flat areas that show up, and that's true of the Wind River in Wyoming. Here you can see, here's the flat floodplain here, here's a former floodplain that's a little bit higher here, and there's a former floodplain here. So these are kind of what we refer to as stream terraces. Okay, deltas. Deltas are when sediment reaches the ocean and rivers reach the ocean, their velocity slow down, and then just barf all their sediment right there where the ocean meets the river. Okay, and what happens is that dying current, that slowing velocity, deposits foreset, topset, and bottomset beds. Okay, the size of sediment varies in the delta. Coarse sediments are deposited closer to the river mouth. Finer sediments make it out further to the bottomset bed area, so deposition occurs. And a delta kind of grows outwards, and it kind of adjusts the stream's gradient, and it continually decreases until the channel becomes like choked up with sediment because it's deposited so much stuff that it diverts, okay? And it seeks a shorter route to the ocean. And so those are called distributaries. So that's how a delta kind of evolves over time. You start off with the river just dumping out and depositing sediment here, and then it chokes itself, finds a shorter path, steeper path to the ocean. That chokes itself, finds a different path, has multiple paths, and then you get a bunch of distributaries, and this collectively is what a delta is and how it evolves over time. And remember, it can get choked over here and then find a new pathway over here and start creating the same pattern in a different area. And then here's a cross section. So you can see here are the top set beds here, the beds that are depositing right onto the ocean. Finer material are the bottom set beds here, and you can see all of this is deposited material from the river. Our most majestic delta is the Mississippi River Delta, and the present day location of the delta where active deposition is occurring is called the Birdfoot Delta. Okay, and that's been doing its thing for the past 500 years. Let's take a picture of that. It looks like a bird's foot, like a crow's foot, right? Caw-caw! There you go. So those are all the distributaries and new sediment that's dumping out into the ocean. But essentially the entire state of Louisiana is an area of unconsolidated sediment and former areas of the Mississippi River Delta. Over the past 5,000 years, these are all the different locations of the river deltas that have been forming. Location number 1 is the oldest, then it hopped over to 2, then to 3, all of the sediment deposited here, then to 4, to 5, and then to 6 here, right? So these are evolving deltas, and this land area is kind of changing really quickly. And what you noticed about the location of the first delta is that now it's mostly inundated by the ocean. And it's because it's no longer receiving as much sediment as it used to. And so as sediment settles in a delta, it sinks. And that's why New Orleans is so susceptible to flooding. In fact, some areas of New Orleans are below sea level because it's no longer receiving sediment from the Mississippi River, and it's sinking because the sediment is settling. That's why it's susceptible to major storms like hurricanes. All right, there are natural depositional features from rivers. One are called natural levees. Levees or natural levees are just raised area that are adjacent to the channel. Okay, And they form during flood events. So when there's flooding and water overtops the banks, it flows out like a flat sheet, and it loses velocity and deposits all its material kind of closest to the river's banks, essentially, or it's right adjacent to the channel. All right, and then the fine materials laid out on the valley floor. All right, and these two features, let me show you a picture. So here's a cross section of a river. This is during a flood event. So, oh my God, the floodplain's flooded. So the coarse sediments will deposit right alongside the side of the channel here. And then fine sediments will grade out further away you go. And so what that is, it creates a structure called natural levees. Okay, and if you have repeated flooding, here's another flood, you deposit more material and you raise those natural levees. So it's nature's way, it's like a catch-22. Nature's like, well, if, you know how you prevent flooding is by flooding. The more you flood, the less you'll flood in the future, right? Because the more often you have flooding, the more you'll have natural levees built up, and then you'll prevent flooding in the future. So it's a weird catch-22, nature's catch-22 there for flooding. But I mean, it's a floodplain. It's supposed to flood. It's a natural phenomenon. And so you can have Yazoo tributaries, small tributaries, like near rivers, and then back swamps or other features that form, or natural features that form as a result of flood stages. Alluvial fans are other depositional features that form from rivers. They're essentially a fan-shaped deposit of sediment. They typically form in really dry areas and mountainous areas. So these are ephemeral rivers. They only run during certain times of the year. And so what happens when there's a rain event and a lot of this water kind of comes down down the mountain, it'll kind of spew out at the bottom of a mountain, and then the water will dry up, and then it'll dump all its sediment in the valley. Let me show you what that looks like. Here's an example of Death Valley in California. So the few times it rains a year, all that water will be diverted towards the valley in this direction. And then all the sediment will be deposited out in this fan shape. And so it's a depositional feature. So here's your higher elevation, you're going down elevation in this direction to the valley floor. So it's just a huge depositional feature created by the events of running water down a mountain front. All right, let's talk about floods. A flood occurs when the stream exceeds the capacity of the channel. So it overtops the channel and then floods an area. This is the most common and destructive geologic hazard. They mostly happen in the spring when we have spring melts. But there's 4 common types of floods. Okay, regional floods, the most common. Flash floods, dangerous. Ice jam floods, in my opinion, not so common. Well, especially because we live in Florida. But in other places, I'll show you some examples. But there can be dam failure floods as well. Regional floods, this is what we deal with every spring. Or it could be a hurricane or something that dumps an unusual amount of water in a short period of time in an area. And then this water overtops the banks and floods a floodplain, for example. Here, the Mississippi River in 2011 flooded this area, and it causes a lot of property damage. And a lot of people can lose their homes, and some people can lose their lives as a result of this type of flooding. Flash floods occur with no warning. They're rapid rises in water levels that can devastate an area or have really fast flow velocities. This occurs in mountainous areas and can also occur in dry areas, the narrows, like I talked about before at Zion National Park. If it rains there, which it doesn't often, but if it does, a lot of that water is diverted through that channel, and those areas that had like 2,000 feet vertical slot canyon area, that the water levels in those rivers can rise like 20 feet in a matter of 15 minutes. So that can be kind of dangerous. The example in the book is of Hurricane Irene. I don't know if you remember that. In 2011, there were flash floods in New York and Vermont. So look at this. This caused a lot of damage to road segments, nearly 2,000 damaged road segments. Imagine if this was 192 in St. Cloud, how long that would take to finish. Construction, my God. Almost 300 damaged bridges, 800 damaged homes. Here's data from a local river its river stage is typically 4 feet, but during the maximum height of the river, it reached almost 18 feet. So that's an increase of 14 feet. 14-foot increase on the river stage is incredible. So that causes a lot of flooding. Ice jam floods are, this occurs in rivers that have natural ice dams. So this occurs in very northern regions. So the example in the book is they give you north flowing rivers in Russia that kind of flow towards the Arctic. And so the headwaters of these rivers are at lower latitudes. So the water warms up first there, then warm water kind of flows downhill northward towards cooler areas. And so then that warm water runs into frozen water, and that water can break those ice dams and then cause flooding behind those ice dams. So those are ice jam floods. Okay. And then there's dam failure floods. This can happen anywhere. Lake Okeechobee had a dam failure flood in the 1920s that flooded South Florida. But large amounts of water can be released in a flash if there's any failure of a dam. Okay, so here's that northern part of Russia. These rivers flow northward, right? And where these river headwaters are, it's warmer here than it is over here in the Arctic Ocean. So sometimes, like an area here, this river could be blocked because of ice, right? And then the warmer waters come into contact and melt the ice dam and then can flood a region over here. So those are ice jam floods. All right, when we talk about floods, we refer to them as like a 25-year event, right? Or a 100-year flood. And what that essentially means is it's an estimate of how often a flood of that size is expected to occur. So a 25-year event is a flood that is supposed to occur once every 25 years. Those are the odds, okay? But you can have 2 back-to-back 25-year events or back-to-back 100-year events. And what a 100-year flood means is essentially like any given year, a 100-year flood event has a 1% chance of any given year of occurring. So we can make those estimates if we've got good data. And good data is 20 to 30 years of stream gauge data, understanding the ebbs and flows of local climate with rain and low pressure and how often the river floods and all that is great. So the more data you have, the better you can predict how often these flood events will occur, because they're going to occur. But what's harder is that because our planet is warming, a lot of times the past historical data cannot predict what will happen in the future, because our hurricanes are holding more water and our low pressure systems are holding more water in the atmosphere. So the rain events are more intense. And so sometimes it might be a bad estimate. A 100-year flood or a flood of that size may actually occur at a higher percentage than 1% because of global warming. And how do we control these floods? What we do is we use artificial levees. We create structures on the top or banks of rivers. So instead of waiting for nature to flood and create natural levees, we just build on the sides of the channel to kind of help the water flow outwards, or we channelize them. That's essentially just digging up the river bottom, and what that does, it makes the river narrower and deeper, and that more efficiently moves water to the base level. That's what we do in Florida. That's why we built canals. That's essentially channelization. We created channels. We just dug narrow, low-lying areas, straight and deep, and that allows water to kind of efficiently drain out and go towards the ultimate base level. So that accelerates erosion. So here's an example of another flood, the Birds Point, New Madrid floodway that had a failure and that caused flooding here. Absolutely devastating. And then there are flood control dams. And I'm sure you've seen this driving around Florida. You'll see some of the canals will have little flood control dams that are there. They can be lifted and lowered. It's all part of the water management. Sometimes we want to hold water during drought, and a lot of times if it's raining a lot, we'll open up those dams to let the water just flow out into the estuaries and into the ocean. But the best approach is the non-structural approach. We should have limited development in floodplain areas, because Floodplains are high-risk flood areas, and why are we going to pay insurance for areas that we know are going to flood at some point? Maybe we should just not build in floodplains that flood often, and avoid just those natural disasters. Okay, bye.